Hey everybody, it's time to put everything together, our algebra and our calculus knowledge, and use all of those skills to analyze a function fully. We're looking at f of x is equal to negative 2x plus 1 divided by the quantity x minus 3. So we'll start with the domain. In this case, we have a rational function, and because we have a fraction, we definitely know that the denominator cannot be equal to 0. And in this case, that would happen if x was equal to 3. So we know x cannot equal 3, and to write that in interval notation, that would be all real numbers except for 3. So that is from negative infinity to 3, and from 3 to infinity. So something's happening at 3. 3 is not in this function's domain. Now, since we ultimately want to create a graph without using our calculator or Desmos or any graphing utility, we want to find the x and y intercepts. So remember that when you're finding the x-intercept for any function or any curve, we're letting y equal 0. So in this case, we're solving 0 is equal to negative 2x plus 1 divided by x minus 3. And that denominator, that x minus 3, of course, if we multiply it over, 0 times x minus 3 is 0. So we're really just looking at the negative 2x plus 1 and solving that equal to 0. So subtract the 1 and divide by negative 2, and we're going to end up with 1/2. So we know we have an x-intercept of 1/2. I'll write that as a coordinate. That's 1/2 comma 0. For the y-intercept, where this graph crosses the y-axis, we know that x must equal 0. So we'll substitute in 0. We're finding f of 0. And we know that's going to end up giving us 1 over negative 3. So negative 1/3. Again, writing that as a coordinate. When x is 0, y is negative 1/3. So you can see the x and y intercepts are not very large numbers. That brings me down here to the graph, which I have a blank xy axes here without any tick marks, but it doesn't appear that we're going to need very large numbers. So I'm just going to preliminarily put some tick marks out here just to get me started. I can make adjustments later, of course. And I will plot, I like to graph as I go. I'll go ahead and plot my x and y intercept. So we had 1/2, comma 0, and then we had 0, negative 1/3. So I'll estimate those two coordinates on my graph. Very good. Let's move on to symmetry. So symmetry can save us some time when we're graphing a curve if we know that it has either y-axis symmetry or perhaps origin symmetry. So remember that when you are testing for symmetry, you're going to substitute in negative x into your function, and you're going to see what you get out and how that compares back to the original function. So I'm subbing in negative x, and that's going to give me negative 2x plus 1 divided by negative x minus 3. So now I'm comparing this result with the original function up here to see if these are the same or if they are opposites or perhaps neither. So a little review here. If you are testing for symmetry and you substitute in negative x and the result is the same as the original function f of x, then that means you have an even function. And even functions have y-axis symmetry. So looking at my result here, it is not the same as the original function. Therefore, this is not a function with y-axis symmetry. If I were to substitute in a negative x and the result was the opposite of the original function, then that's an odd function, which means that we would have origin symmetry. But again, looking at the result, it is not the exact opposite of the original. Therefore, this curve does not have y-axis symmetry, and it does not have origin symmetry. So we're just going to write that we don't have any symmetry. We'll write none. Moving on to asymptotes. Now here's where a calculus begins. For the asymptotes, we've got to look at the limits. So let's start with the horizontal asymptote. So looking at the far right-hand side of the graph, that would be the limit as x approaches infinity of negative 2x plus 1 divided by x minus 3. So thinking about x values getting infinitely large, if that were to happen, you could see if I were to have a very, very large number substituted in for x, we'd have a very large number times negative 2. That's going to be a very, very large negative number. So the numerator is approaching negative infinity. The denominator, if we have a very large number substituted in for x, a very, very large number, minus 3 is going to continue to be a very, very large positive number. So we have negative infinity over infinity, and that is one of our indeterminate forms. So this is going to be a limit that we can compute utilizing L'Hopital's rule. So I'll put a little L over the equal sign to indicate that I'm using L'Hopital's rule, which allows me to take the derivative of the numerator, which is negative 2, and divide it by the derivative of the denominator, positive 1. So this ends up being the limit of negative 2, and the limit of a constant is the constant. So because we got a value here of negative 2, as x gets infinitely large, our y values are approaching negative 2, and that tells us that we have a horizontal asymptote, and it's the horizontal line y equals negative 2. So for a horizontal asymptote here, I'm going to write y equals negative 2. And then we need to move on to a vertical asymptote, which is a different ballgame. So a vertical asymptote may occur. However, we've got to look at the domain again, and the domain up here said x cannot equal 3. So we're not sure what's happening at 3. Some options, we might have a vertical asymptote. That would be an infinite discontinuity. But we also might have a hole or a removable discontinuity. So we really don't know what is happening unless we dig deeper and look at the limit as x approaches 3. 3 is that value that makes the function undefined, so we're going to look at what's happening as we approach 3. Now, to be a vertical asymptote, we would need to have our y values either getting infinitely large or infinitely small. So we really don't need to analyze x approaching 3 from both sides. We could just analyze x approaching 3 from one side or the other. So I'm going to go ahead and just choose x approaches 3 from the left. And then again, our function, which was the negative 2x plus 1 divided by x minus 3. All right, so this is not a situation where you can do L'Hopital's rule because we do not have an indeterminate form when we substitute in 3. So we really just have to sort of think about this logically. You could call it numerically, think about this limit, because we're basically thinking about what's happening to this function if we're looking at values that are smaller to 3, but very, very, very close to 3. So for example, if x was, let's say, 2.9, that's smaller than 3, but very, very close to 3. So if you can imagine, and you don't have to write this down, but you're just thinking, if you were to substitute in 2.9 into this function, we're just thinking about the behavior of the numerator and the denominator and what's happening. So in the numerator, we're going to basically end up with a negative number. So I'm just going to put a negative on top. Now in the denominator, we have 2.9 minus 3, and that's also going to be negative. So we're going to have a negative divided by a negative. But specifically, we're dividing by a negative number that is small because it's negative 0.1. And dividing by negative 0.1, that's dividing by negative 1 over 10. That would cause us then to multiply the entire thing by 10 because we would divide by a fraction and change it to multiplying by the reciprocal. So even though we're dividing by a negative and we know the ultimate result is going to be a positive, it's going to be a rather large positive number because we're dividing by a fraction. So the limit as x approaches 3 from the left will end up being positive infinity. And that is enough proof to show that we do have a vertical asymptote at x equals 3. So I'll come back up here and I'll list the vertical asymptote, the vertical line x equals 3. And then I would encourage you to go ahead and go down to your graph and let's begin to plot these characteristics. So that vertical asymptote was x equals 3. I like to do my asymptotes in a different color. And my horizontal asymptote was y equals -2. All right, now we're on to increasing, decreasing, maxes and mins, as well as concavity. And since we're finding everything here, it might be useful to remember that increasing, decreasing, max and mins, that can all be determined from our first derivative. And then our concavity and inflection points can be determined from our second derivative. So we'll be doing our first derivative test to start us off. And at this point, you're thinking, oh my gosh, I'm running out of room. And I would say, yes, we need a full page, maybe even a little bit more space if we're going to do this full deep analysis. To determine the derivative of this function, we are going to use the quotient rule. So quotient rule says we take that denominator, x minus 3, multiplied by the derivative of the numerator, low d high, derivative of the numerator is -2. So that's low d high minus high, the numerator, which is -2x plus 1, times the derivative of the denominator, which is just 1, all divided by that denominator squared. So simplifying here, it looks like we're going to have -2x plus 6 plus 2x minus 1, all divided by x minus 3, the quantity squared. So our simplified first derivative is going to be 5 divided by x minus 3, the quantity squared. And remember, once we have our first derivative, then we are going to find our critical numbers. So critical numbers are numbers where the derivative will either equal 0 or where the derivative is undefined. And in order for a fraction to equal 0, the numerator would have to ultimately be 0. But the numerator of our derivative is 5, not 0. There's no way for us to make this function equal 0. So the derivative will never equal 0. That tells us that our function, our graph, it's not going to have any horizontal tangents. However, we know that this derivative will be undefined if the denominator is equal to 0, and that will only happen if x is equal to 3. Now, technically, 3 is not considered a critical number because it is not in the domain of the original function. So if we go back up here and we look at our domain, remember, x cannot equal 3. So 3 is not in the domain of the function. It's not considered a critical number. However, it is important that we test our first derivative on both sides of 3 so that we can determine whether the function is increasing or decreasing on either side. So we are going to test a number smaller than 3. 0 is a nice choice, and a number larger than 3. And remember, that test is occurring into the first derivative. But save yourself a little time. Notice that the first derivative, we're dividing by x minus 3, the quantity squared. So this denominator will always be positive. So that tells us that when we plug in 0 and if we plug in 4, both of those are going to result in a positive first derivatives. So that tells us that this function is always increasing. Since the slope is positive, the function's always increasing. And we don't have any maxes or mins because we don't have a change in sign on the first derivative. But rather than write always, I'm going to say it's increasing from -infinity to 3, union 3 to infinity. I don't want to include 3 in this interval because remember, 3 was not in the domain of the original function. So it's going to be increasing over its domain. It will never decrease. And then we don't have any local maximums or local minimums. First derivative is done. So now we move on to the second derivative, which I'll do in blue. So again, we got to do the quotient rule a second time. So low is x minus 3, the quantity squared. The derivative of 5 is just 0. Low d high minus high is 5. The derivative of the denominator, we're going to do our chain rule. So 2 times the quantity x minus 3, technically to the first power, multiplied by the derivative of x minus 3, which is just 1, all divided by the denominator squared. So it is already squared and getting squared again, so it's to the 4th power. That simplifies pretty nicely since we have this whole quantity times 0. So we're looking at negative 10 times the quantity x minus 3 divided by x minus 3 to the 4th power. And then we can simplify and divide out an x minus 3 with one of our x minus 3's in the denominator. So we're looking at a simplified second derivative of negative 10 divided by x minus 3, the quantity squared. Very good. So now we've got to do the same analysis, but we're analyzing the second derivative this time. So we can determine the intervals where the function is concave up and concave down, and therefore some inflection points, if there are any. So again, the second derivative would only change sign where the second derivative is equal to 0 or where the second derivative is undefined. So we're repeating the same process, but on the second derivative this time. Second derivative will never equal 0 because, again, the numerator would have to equal 0, and currently our numerator is just negative 10. There's no way to make that equal 0. The second derivative is undefined if the denominator is equal to 0, and once again, that would happen only if x is equal to 3. So we'll do our sign analysis, but this time our sign analysis is for the second derivative. So we're going to test a number smaller than 3, something larger than 3, and again, we're testing these values into our second derivative. Notice again, the denominator of our second derivative, and I just saw a little mistake there. Many of you probably already caught it. This I wrote as a 2 right there, my apologies. Rather than re-recording that, that should have been a 3. I'm glad I caught it because that is going to make a difference when we do our testing here. So the numerator is going to be negative 10 no matter what. So I'm just going to put a negative sign in the numerator. Then our denominator, if we substitute in 0, we're going to end up with 0 minus 3, so negative 3 cubed, and that will be negative as well. Negative divided by negative is a positive. Then again, if we plug in 4, the numerator is still negative 10, but 4 minus 3 is positive 1, and if we cube that, that will give us a positive. Negative divided by a positive will be a negative. Now be careful here, because we do have a change in sign on our second derivative. And if we're rushing through, you might think that we have an inflection point, because typically inflection points are where the second derivative changes sign. But remember, 3 is not in the function's domain. In fact, 3 was the location of the vertical asymptote. So we're not going to consider 3 an inflection point because it's not actually a point on the graph. There's a vertical asymptote there. So there's no inflection points, but we do have a positive second derivative, which means that the original function, f, will be concave up like a cup, from negative infinity to 3, and then a negative second derivative tells us the original function f is concave down from 3 to infinity. So going back in here, we don't have any inflection points. We'll write none. And again, we are going to be concave up on the interval negative infinity to 3, and then concave down on the interval 3 to infinity. Well done, we are almost through this monster problem. Now we just want to put the puzzle pieces together, and we have most of them. We just need to create our graph. So I'm just going to notate sort of underneath my graph here. We just found out the concavity. So we said from negative infinity to 3, this portion of the graph is concave up. And then from 3 to infinity, this portion of the graph is concave down. And then if you look back at our first derivative, increasing and decreasing intervals here, remember we said the graph is always increasing. So I'm just going to make myself a little note, INC for increasing, and it increases the entire time. So I need to draw a branch that is concave up and increasing, and then remember it's also going to be approaching these asymptotes. So that would have to look something like this. Try to smooth it out and then hug your asymptotes. So that is concave up like a cup as well as increasing. And then we would need another piece that would have to be down here. And again, this is concave down, but also increasing. And if you're questioning why I chose to put the other branch down here, sort of in the bottom right quadrant, if you think about it, I could not have a piece that would go here, because if I did, I would have another x-intercept. And we found all of the x-intercepts, there was only one. There's not a second x-intercept, so we can't have a branch there. In addition, of course, what I just drew, that would be decreasing, not increasing. So it makes sense for the branch to be where we originally drew it.